To the next Sydney CPPC seminar. So our today's speaker is Seth Koren from the University of Chicago. Seth got his PhD from the University of California, Santa Barbara. His supervisor was Nathaniel Craig. And after his PhD, he moved to the University of Chicago. Seth has been working on a variety of topics, and most recently, he has been working on those generalized symmetries and to put them to use in particle physics. And I'm very much looking forward to hearing about that today. So over to you. Take it away.
Great. Thank you so much, Michael. And thank you for the invitation. As I was saying before we started, I've always felt like my research program has somewhat of an Australian flavor in terms of some of the models and topics I've been interested in. So I'd really like to visit in person sometime, but a great first step is talking virtually. And I'm happy to tell you about this work I've been doing that I found quite exciting with some of my collaborators, primarily Clay Cordova and Sungwoo Hong, also Kentaro Omori at Tokyo, and I'll mention a bunch of other things as we go through. So the big picture here is that I come to you as, I think, a harbinger to tell you that there has been an interesting line of work in the land of formal theory over the past decade, that is, which has reformulated our core notion of global symmetries in field theories in a way that has allowed for lots of interesting generalization. And as to why some generalization is needed, what you can have in mind, I think, is just the notion of higher form symmetries. Very briefly, if you recall when you learned about global symmetries in your quantum field theory textbook, these were some transformations on local fields or particles, some zero-dimensional operators. And that's all well and good. But then now that you understand deeply more quantum field theory, you know that very frequently field theories we care about as particle physicists have extended objects in them, right? We've long appreciated that understanding the behavior of Wilson lines, some one-dimensional operators, is important for understanding gauge theory. And theories we care about often in the early universe produce things like cosmic strings or domain walls. So it's a natural question in this background as to whether there is a notion of global symmetry which exists for these extended operators. And the answer is yes. In this more general framework of higher form symmetries, those familiar global symmetries from your textbook are zero form symmetries. They act on zero-dimensional operators like particles or local fields, and they have some conserved one index current. But if our theory has some Wilson lines or some 't Hooft lines, you can think the world line of some very heavy monopole, these are one-dimensional objects that can have a notion of one-form symmetry. And they have an associated current with two indices that still obeys a current conservation equation. And one-form symmetry will really be the main player for us today, and what we can learn from it being intertwined with zero-form symmetry for model building, and I'll get to. But you can have a notion of higher form symmetries for whatever sort of dimensional objects you have. There's an associated current with more indices. Okay, now, you know, formal field theorists talk about a lot of things, and they're very interesting in their own regard, but most of the time as particle physicists, we know that we can just sort of ignore them. But of course, the notion of symmetry is something that's central to many questions that we have as particle physicists. So I think that for some years, people had been asking whether there was anything for us to learn from this program in particular. And I'm happy to say that I think my collaborators and I have shown that the answer is yes. Now what might you want what might you ask of this program as a particle physicist? To start, you want to know if there are actually these more exotic, subtle notions of symmetries in models that we care about as particle physicists, not just some 1+1 dimensional lattice of spins or something, where a lot of the study has been. And indeed, it turns out that the standard model itself has a higher flavor symmetry structure. We're going to go beyond. We're going to generalize beyond from zero form to higher form symmetries, but from group-like transformations to more general transformations that you can have. And if we go beyond the standard model and we gauge an additional U1, in fact, frequently you find that those models have non-invertible symmetries, another type of symmetry I'll get to. But more so than these symmetries just being present in models we care about, what you'd really like to know is it worth the time to understand them? By understanding these symmetries, can you gain any further insight into these models, any new perspectives? Can you learn something about the ultraviolet of these models? And again, I think the answer there is yes. In fact, this higher flavor symmetry in the standard model controls which standard model fermions from the infrared might end up in the same multiplet in some unified theory. And in fact, okay, sorry, this my slides are a little bit in flux. In fact, I'm only going to mention this first point a bit. Really, today I'm going to focus on the second point, that when you find a non-invertible symmetry in your infrared model, that can reveal some interesting model building opportunities in the form of some UV theory, where some symmetry is broken only non-perturbatively. You have some reason for an exponentially small violation of a symmetry. And that's what I'm really going to focus on today. Apologies, I thought that by now I'd have another paper out on this topic. I'm still going to try to talk about what that forthcoming work is, but the paper is not quite out yet. But hopefully we'll get there. Great. So as I said, the main sort of new concept that I'm going to talk about is one-form symmetry. So I want to go over this a bit, and mainly just to tell you that, you know, this is maybe a little bit scary language, but really it's something that you're mostly familiar with, just with some new language that will help us get a bit farther with it. And indeed, the simplest theory of particle physics that has one-form symmetry is just pure electromagnetism, the theory of the photon. And in fact, you already know from undergrad, say, that this theory has two, in fact, conserved two-form currents. I'm just going to assert to you that there really is a notion of one-form symmetry that you should think about with them. In particular, if you look at the equation of motion of the photon, then that takes the form of a two-form symmetry current conservation equation, with the two-form current being the photon field strength itself. That really is that there's a notion of an electric one-form symmetry in this theory, and that electric one-form symmetry measures the charges, in fact, of Wilson lines. Again, this big language, but really something you know from undergrad. This is just Gauss's law. When you went and measured the charge, the electric charge, by drawing some Gaussian surface around some charges, manifestly that wasn't, you weren't computing a Noether charge for some familiar zero form symmetry, right? Such a Noether charge would be an integral over all of space at a given time. Rather, you were doing an integral over a two-dimensional manifold. That's because you were really measuring this electric one-form symmetry charge, right? The integral to get the conserved charge is of the photon field strength over this two surface. Okay, so really this one-form symmetry is something quite familiar, and good. What you should think about, just to slightly further connect it, in this more relativistic picture, what you should think about is that the spatial location of the heavy charge that you are surrounding with your Gaussian sphere is really the place on that time slice where the Wilson line sort of intersects that time slice. You really were measuring the charge associated to a Wilson line. And sort of dually, electromagnetism, because of the Bianchi identity, you might say, has a second two-form conserved current, which is just a Hodge dual of the photon field strength, and that really has a magnetic one-form symmetry associated to it that measures the charges of 't Hooft lines. Of course, if you wanted to, you could put together a dual version of Gauss's law to measure those magnetic charges. Good. Okay. Now, one-form symmetry. There's an interesting question and a stark difference between zero-form symmetries and higher-form symmetries is in how they can be broken. Now, when you have a to remind you, when you have a zero-form symmetry, when a normal symmetry, when the charged objects are local operators, you can break that symmetry explicitly by just adding some charged object to the Lagrangian, right? If I write down a Majorana mass for neutrinos, it breaks lepton number. But these higher form symmetries are a notion of symmetry where the charged objects are not local operators. They are extended operators. And so there's nothing I can't add any operator to the Lagrangian to break this symmetry. If I deform Maxwell theory with some higher dimensional operators, all that will do is maybe modify what the electric one-form symmetry current looks like in terms of the photon field strength, but it won't fundamentally break the one-form symmetry. It can't, because no local operator is charged under the one-form symmetry. So then how do you break higher form symmetries? Well, the way to do it is you need to add some dynamical charges. Breaking a higher form symmetry requires modifying the degrees of freedom in your theory. This is obvious enough at the level of the current conservation. If you write down the photon field strength, once I've added in a finite mass electron, then of course there's no longer that conservation. You have the current on the other side. Maybe a good way to think about it, if you've thought much, if you like topology, you can think that now if you draw a Wilson loop, now that Wilson loop can decay to, it's unstable to pairs, producing pairs of positrons and electrons. They can end now, now that you have a dynamical charge. Or maybe, saying roughly the same thing another way, just to connect more, is really you should think about this in terms of the physics of screening. Once I have a finite mass electron in my theory, then really Gauss's law breaks at small distances. If I bring my Gaussian surface to within an electron Compton radius of my heavy charge, then that Gaussian surface is sensitive to loops of positrons and electrons that dynamically screen the charge. This is nothing other than the one loop photon polarization from QED 100 years ago or so. Okay, so it really is the new degrees of freedom that you add that break this symmetry. Just to repeat, in the real world, in the far infrared, below the mass of the electron, there are no charged particles, and the real world really does enjoy an emergent one-form electric symmetry. That's why Gauss's law works. But when you go to higher energies and you see that we have charged particles, the one-form symmetry is broken. Gauss's law is broken. Okay, and this is going to be a key point in the model building use we're going to make out of this. In particular, for the magnetic version, when you have a magnetic one-form symmetry, likewise, it's going to be broken at scales where you're sensitive to loops of magnetic monopoles. And we're going to find some interesting model building usage by finding some scenario where a higher form symmetry, a one form symmetry, is intertwined in some way, and I'll get to what I mean by that, with a zero form symmetry. And then we'll learn about the fate of the zero form symmetry when that one form symmetry is broken by some new degrees of freedom in the UV. Yeah, was there a question?
Can I ask a quick question? So what happens in the massless electrodynamics? Is that the symmetry, broken at the infrared, or?
Yeah, if you have a massless charged particle, then there's never an electric one-form symmetry. That's right. Yeah, you have these long distance loops of charged particles that
related with the infrared divergences.
Sorry.
Related with the infrared divergences of the theory. It's a sick one anyway.
Yeah, true. That would be a difficult theory to define precisely. Yeah, related, definitely.
Okay.
Good. Cool. Okay. So, good. Before I get to some BSM usages, I thought I would start by going over the generalized global symmetries of the standard model as a good way to sort of set the stage, and also to give you a basic scope of maybe interesting further things to think about for where this could impact our understanding of the world. So let me, I should say, the standard model I have here, as you know, 3 generations of each of 5 different Weyl fermions, along with the Higgs. And I'll note that I've normalized the hypercharge in what I'll say is the correct way, but the prescription is that the least charged particle should have unit charge, which for us is the left-handed quarks. Okay, so what are the generalized global symmetries? Let me start with the one-form symmetries enjoyed by the standard model. Now, as you know, we don't have any magnetic monopoles in the standard model. So 't Hooft lines, 't Hooft loops cannot end on anything. And indeed, we have a magnetic one-form symmetry for hypercharge. Now, how about an electric one-form symmetry? Well, we have hypercharged fields, all of them, but it turns out that the hypercharges and the non-abelian charges of the fields are arranged in quite an interesting way, such that it's possible there is some discrete electric one-form symmetry in the standard model. We actually don't know. This is related to the global structure of the gauge group of the standard model, which was written about very nicely, clearly by David Tong a few years ago. But if you haven't heard that story, the point is that there are certain center transformations which actually don't act on any of these standard model fields. What you can consider is, imagine a Z2 subgroup of SU2, the center subgroup of SU2. The non-trivial element there just multiplies all of the electroweak doublets by -1. It's the center of SU2. And I can also consider a Z2 subgroup of hypercharge, just a pi rotation. Now, you'll notice that all of the standard model fields that are electroweak doublets have odd hypercharge. And so they pick up a minus sign under both of these transformations. They transform the same way under each of them. And so together, they stay the same. It's the identity. And it so happens that all of the right-handed, the SU2 singlets happen to have even hypercharge. And so they don't transform under either one of these factors. So it turns out that this combination of Z2 symmetries that lives together between SU2 and U1Y actually doesn't act on any of the standard model fields. And the point is that as a result, maybe it's not really part of the gauge group. Maybe the proper gauge group should identify. You don't actually have the freedom to do these 2 different rotations separately that happen to line up. Maybe you should identify these two elements, the center of SU2 and Z2 of U on Y. And there's an exactly analogous story about the Z3 center of color. And together, this means that we only know the standard model gauge group. We know what it is locally. We know the algebra. But the gauge group has a Z6 sort of ambiguity. There can be an overall modding out by this, the center of the gauge group. You can mod out by Z6 or just a subgroup, 3, 2, or nothing, 1. And if the gauge group does not have this Z6 modding, then in fact there is a discrete electric one-form symmetry of the standard model. That is, if these are really separate rotations that I can do, then if there's nothing charged under them in the standard model, that corresponds to some Wilson lines that don't have anywhere to end, some electric one-form symmetry, but only a discrete amount. And I wanted to mention this, because this concept is going to come up in a BSM context at the end of the talk, in future and in my forthcoming work. And also, I'll mention that somehow people have really only thought about this a little bit in very top-down ways. And you can just imagine, you could sort of think about learning about this from the bottom up. If we discover the next particle, when we finally find the vector-like spectrum under the standard model, now that we've discovered the chiral spectrum, if we measure the next vector-like particle and it's not consistent with this Z6, say it only transforms under this Z2 of hypercharge, that will tell us about the global structure of the standard model gauge group, and will really restrict for us which possible grand unified theories. It tells us about physics at arbitrarily short distances. And so I'm Adam Martin at Notre Dame, where I'll be in 2 weeks, are thinking about that. It's an advertisement for some future work. Now, further, okay, that's the one-form symmetries of the standard model. The zero-form symmetries, as you know, just writing down the matter content, you start with this large U3 to the 5th flavor symmetry. Ng equals 3 is the number of generations, classically at least. But when I go and write down the Yukawas, those, of course, explicitly break most of this flavor symmetry. Overall, there's a leftover classical, as you know, separate baryon and lepton rotations that, in fact, get broken by electroweak instantons down to, well, the only continuous factor is baryon minus lepton number. But I'd like to mention that, in fact, there is also an exact discrete subgroup of lepton number that remains, well, again, an exact symmetry of the quantum standard model, because we have more than one generation. And in fact, it's that factor, and the fact that we have more than one generation, that means that the proton in the standard model is exactly stable. I wrote a short note on this last year, just because I think some experts knew this, but it was not anywhere clearly communicated. And finally, well, okay, and it's interesting to say, in light of 40 years of disappointing proton decay results. Okay, but I mentioned, well, finally on this slide, I mentioned that, as you know, the standard model proper, and what I'll mean by the standard model with massless neutrinos, has exact lepton flavor difference symmetries, but in fact, having discovered neutrino masses and measured the mixings, we know that these are not a symmetry of the real world, only an approximate symmetry. Now, what else with these approximate zero-form symmetries I'd like to mention, although I don't have time to really go through this at any depth, you can consider this another advertisement, but the non-abelian flavor symmetries, in fact, are intertwined with the magnetic one-form symmetry of hypercharge in the form of a more subtle structure known as a two group. And I explored this with Clay last year. In fact, that's that structure is encoded in triangle diagrams like this, with two global legs and one gauge leg, which you could have always calculated in the standard model. Standard calculation, really just counting the zero modes to find these coefficients here. But previously, you just didn't know what to say about this sort of triangle diagram. And in fact, you can find a quite interesting conclusion, from the general understanding of two-group appearance in field theories, which was laid out, I should say, by Clay and Dumitrescu and Intriligator in, I think, 2017, 2018. Any zero-form flavor symmetry that is intertwined has some non-zero coefficient with hypercharge in this way, in fact, must be broken at the scale of a UV completion that introduces magnetic monopoles. The only ones which are allowed not to be broken by such a UV completion are diagonal combinations of these symmetries that in total have zero coefficient with hypercharge, and that means, well, the realization was that means that in the context of some weakly coupled grand unified theories, you can read off from the infrared the possibilities for what infrared standard model fermions might end up in the same gut multiplet. And in fact, there are only a few sorts of possibilities. That's what you learn strictly at zero Yukawa. With finite Yukawa, in fact, maybe even more interestingly, you can think of the Yukawas as spurions, in fact, of this entire two-group structure. And this strict, very limited possibilities for the multiplet structure at zero Yukawa can in fact be perturbed away from if the Yukawas that break the zero form part of this two group control in the UV the mass of some vector-like fermions. So I think there's more to be explored in this direction. So I wanted to mention it, but it's not going to be the main focus of this talk. One final sort of still in the global symmetries of the standard model, there's sort of another ambiguity, which is, for the same reason that baryon minus lepton number is non-anomalous, it's an exact global symmetry in the standard model. Well, it could actually be a gauge symmetry without adding any new particles charged under the standard model gauge groups. So it's really an empirical question as to whether it's a global symmetry or perhaps a very weakly coupled gauge symmetry. But thankfully, we have fantastic experimenters who've measured all sorts of things, including lots of fifth force constraints. And they tell us, okay, if U1 B minus L was ever gauged, it must have been broken. There's no extra massless boson in the far infrared. But there's still a note of ambiguity, because for that same reason, a discrete subgroup of B minus L could perfectly well be gauged and entirely unbroken. Another gauge symmetry of the far infrared of the world. And this is, in some sense, the simplest possible extension of the standard model you could imagine. It has zero new degrees of freedom, and interestingly, it comes along also with a magnetic two-form symmetry, since when you have a discrete gauge theory, the topological defects carrying magnetic flux are cosmic strings. But somehow there's been essentially zero work on this. I suggested last year that these cosmic strings could help resolve the cosmological lithium problem, because there would be a symmetry that would mean that they only destroy 3 protons at once. So destroying lithium and bringing it down to the levels we need to match observation without messing up deuterium or anything. I'm happy to talk about that offline. Okay, let me actually get to the main topic that I want to talk about. Thank you for putting up with the extended standard model introduction. And that is non-invertible chiral symmetries. And I want to just briefly on this slide tell you the point in advance. In the next few slides, I'm going to at least wave at some field theory about this. But if you don't follow that, it's totally fine. It won't be necessary in the rest of the things. But the point is that for our purposes, what you can think is that in a situation where you have an ABJ anomaly, but there are no instantons on R4 that sort of realize that anomaly, there is in fact a subtler notion of symmetry you can identify, a non-invertible symmetry. And it turns out this sort of symmetry will act both on local operators, like a normal zero form symmetry, but also on Tooft operators, world lines of heavy magnetic monopoles, you can think. And this intertwining will imply that if I introduce magnetic monopoles in some UV completion of my theory, which break the magnetic one-form symmetry, that has to break the non-invertible symmetry. But that breaking is only communicated to really the zero form part of it in terms of generating operators that violate the symmetry. It's only communicated non-perturbatively from loops of magnetic monopoles, you can think. From the infrared. And this will allow us to, by understanding these symmetries, a non-invertible symmetry in an infrared theory, this will lead us to some interesting UV models in which you have extra UV instantons that can resolve some infrared naturalness issues. So that's where we're going. Let me, if there's a quick question, I can also take a question. Okay, good. So as to why some understanding like this is necessary, let me remind you of the following confusing situation. Let's consider we have a global, classically, a global U1 symmetry, and it has an ABJ anomaly. Now, if the gauge group, so the triangle is gauge, global now, if the gauge group is something non-abelian like SUN, then this is very familiar. We know what to do with it. The anomaly breaks the global continuous U1 down to some discrete subgroup. Sorry, I should have said first, current conservation is modified. The current is no longer conserved, but rather you find some FF tilde term on the right-hand side with some quantized coefficient K. The U1 is broken down to ZK, and you really have these non-abelian instantons that dynamically violate the U1 symmetry by K units that tell you it's really ZK. You can think about, for example, electroweak sphalerons, which in the early universe indeed dynamically break U1 baryon plus lepton number down to a discrete subgroup. Okay, but what about the case where it's a U1 gauge group? The current conservation is actually modified in just the same way. So you're tempted to say, okay, the symmetry is broken again from U1 down to some discrete subgroup, CK. But we happen to also know this fact as particle physicists that, in fact, U1 cannot, appropriately wrap the Euclidean infinity. And so there actually aren't any abelian instantons on S4, R4, S4. And so as a particle physicist, your pragmatic attitude is just, well, okay, maybe that's there, but you can just ignore the breaking. In particular, if you only go out and measure, say, S matrix elements, then indeed, you'll find that the full U1 ends up still being conserved. But this is clearly, from the more formal side, a rather unsatisfying theoretical situation. Is the symmetry really broken, right? The current conservation no longer works in general, or is there some notion of symmetry that we can still recover? Because as we know, the S matrix is still invariant. So what's going on? And in the more modern language, the understanding is that indeed, at the level of normal invertible symmetries, the U1 is broken down to ZK, But the rest of the U1 isn't really broken, rather converted into a more subtle type, a non-invertible symmetry. Now, to really explain this in detail would have been a different sort of talk, where I spent the first half of it introducing sort of the language of generalized symmetries. But let me very briefly try to give you a sense of it. The point is that we're going to have to expand our notion of symmetry. And in particular, we're going to give up on looking for conserved currents, because there won't be one in this case, and satisfy ourselves just with some exponentiated charge. So you can think about this as generalizing Noether charges, right? Here I have, if I integrate the 0th component of some conserved current over all of space at a given time, that's just a regular Noether charge. But I can also perfectly well do something more relativistically invariant and integrate a conserved current over any sort of 3-manifold and get a charge operator that lives on a 3-manifold. Here I've drawn in particular a 3-ball in 4 space, and in 4-dimensional space, a 3-dimensional ball wraps or links a point, right? So a point is either inside or outside of the ball. So you can think about the action of this symmetry, what we call it a symmetry defect. You can think about this acting on a charged field by, if you try to move a field from inside to outside the ball, you pick up a factor of the charge of the field. One says, more generally, these symmetry defect operators are topological, except when they cross some charged operators. You can think of this, you really should think of this as just the generalization of that Gaussian sphere, where again, you can move the Gaussian sphere around all you want, as long as you don't cross any charged operators. And this tells you how correlation functions change if you do cross charged operators. Now, we don't quite want just the charge. Really, we want to exponentiate the charge, because it's nice to work with sort of unitary operators when they're available. And the exponentiated charge acts with a finite rotation. Now it depends on some rotation parameter alpha, and it acts as a finite rotation on some charged field when you move from inside to outside. Now, if this were a regular zero-form symmetry, then this would be correct. I would define this. This would be my symmetry defect operator. And this sort of, the way I think about the use of this is it sort of gives you a way of talking about the local effects of global symmetries, in that you can think of a finite symmetry defect operator and what happens to fields in your correlation function if they're on one side or the other, things like that. Okay, so if this was a normal symmetry, zero-form symmetry, we do that. But now we have this anomaly on the previous slide. So this, in fact, is no longer conserved, because with the not modified current conservation, this is no longer conserved in general. So what you could try to do, what people had tried to do long ago, is sort of move the right-hand side over to the left-hand side, and write some sort of Chern-Simons theory, the derivative of which formally gives you that FF tilde term. But really, that doesn't actually make sense, except when you're on, say, R4. But in general, it doesn't. But if you know some condensed matter field theory or formal field theorist friend, they can tell you that there's a way to soup this up, to do this correctly. And that's by defining a more exotic sort of charge operator. In fact, what it turns out you need to do is couple your charge operator to some auxiliary Chern-Simons theory, some degrees of freedom, fundamentally three-dimensional degrees of freedom that live only on this symmetry defect operator you're considering. And I'm not going to go through this because the details are not going to be important for us at all, although I'll recommend these beautiful papers written by my collaborators and also sort of the Stony Brook group, great papers. And what this allows you to do is to good. You're doing a correct version of what we wanted to do on the bottom line of the last slide. And indeed defining some souped up operators that still defines a symmetry of this theory, even with that anomaly. They define a symmetry in that they're still topological, and so they still imply constraints on things like correlation functions. Okay, and really the key player. The key player in some sense is that you have a magnetic one-form symmetry that gets coupled to this Chern-Simons theory. That's how the Chern-Simons theory is able to do anything, coupled to the bulk physics through this magnetic one-form symmetry of your, say, abelian gauge theory. Okay, but again, none of that really, none of that will matter for the things that I'm going to say. What you should just think is that now this upgraded but more subtle notion of charge, in fact, also acts non-trivially on 't Hooft lines, right? We started with a zero-form symmetry, which acts natively on point operators. But we've had, because of this anomaly, we've had to soup it up by adding some degrees of freedom that live on it. And this means that it picks up a non-trivial action on 't Hooft loops. If I start with some 't Hooft loop inside my 3-ball and I bring it out, in fact, it acts on that 't Hooft line by, attaching a surface operator, a sort of monopole operator. But more physically, what you can think is this is capturing, to relate it to something that was sort of known in the past. Physically, this is capturing the fact that in the presence of a magnetic monopole, you can, the monopole provides the topology that can sort of activate these abelian instantons. If you've thought very much about the Kalin-Rubakov effect, that's part of what is going on there. That when you have this monopole world line, you can in fact activate the abelian anomaly. That's how B plus L gets violated in the presence of a monopole. But the cost for having this exotic sort of symmetry, just to relate to the name, is that the charge operator is no longer invertible. It continues to act invertibly on local operators. This is why the S matrix is just invariant under the full U1 symmetry. But the action on 't Hooft loops is more complicated, and in particular non-invertible. There is no inverse operation. You end up doing something non-trivial to the magnetic monopole world line. Okay, again, the details won't be relevant. The simple takeaway is that now we have a zero-form symmetry that's again intertwined with some sort of magnetic one-form symmetry. So imagine I have some local operator that is only charged under, only protected by a non-invertible symmetry. Okay, now consider when I have a UV completion that provides monopoles. If my UV completion provides monopoles, then this breaks the one-form magnetic symmetry. 't Hooft lines can now end on these magnetic monopoles. And because the non-invertible symmetry acts both on local operators and on monopoles, this must break the non-invertible symmetry. And then if there was nothing else protecting that local operator, it must be generated. But the point is that you've only broken it sort of through the presence of these magnetic monopoles. So the way that ultimately gets communicated to the zero-form symmetry breaking, the way it generates some operator, has to know about virtual monopoles. And is automatically suppressed. You can estimate the, where is, oh, there we go. You can estimate the size of this in general with some cute argument. I should say, really, there's this very nice paper by Gigi and Katie and John and Matt, where they did this very explicitly. But if you just think about some weakly coupled UV completion with Tuft-Polyakov monopoles, you expect that an operator you generate in the Lagrangian has to be suppressed by some sort of monopole action. And if you think in a world line formalism, it's just the mass times whatever some appropriate time period for the virtual monopole to pop into existence. In a weakly coupled UV completion, the mass is just the VEV divided by the gauge coupling, and a sensible time period over which a virtual monopole will live is the cutoff of the infrared theory, which is the mass of the W bosons, the VEV times the gauge coupling. And if you plug that in, you'll find, and again, this is just a hand wavy argument, we'll see it concretely in our UV models, but you find sort of from the infrared that you expect some non-perturbative e to the minus some number over g squared breaking of this symmetry. So the plan, given this general reasoning, is that if we can identify an infrared theory that has some non-invertible symmetry, we can then find a UV theory that introduces monopoles, and we'll find that the violation of this non-invertible symmetry is automatically exponentially suppressed. I realize I'm going quite slowly. Let me try to speed up a little. Good. Let's go beyond the standard model and gauge L mu minus L tau. This is very well motivated, but I won't, you probably know that. When we gauge L mu minus L tau, there is another class of triangle diagrams we should look at. And in fact, the other lepton family difference symmetry, that would be a global symmetry, has a non-zero ABJ anomaly with L mu minus L tau. The coefficient is -1. And that means LE minus L mu is turned into a non-invertible symmetry in these theories. And in particular, well, this non-invertible symmetry prevents neutrino masses. The easy way to see that it prevents all of them is if I take LE minus L mu and I subtract the gauge charge, then because -2 is equal to 1 mod 3, in fact, this overlaps with a Z3 subgroup of normal lepton number that acts on all of the leptons. So this theory really has a Z3 subgroup of lepton number, which is non-invertible. Just this, and that really disallows or protects Majorana masses for neutrinos in L mu minus L tau models. And so from this general logic, I should expect that if I write down a UV completion of L mu minus L tau that introduces magnetic monopoles, I will generate only exponentially suppressed Majorana masses for neutrinos. Now, I can read your minds. You're probably not that impressed because we know of some at least well-liked ways to get Majorana masses for neutrinos that are very small. But in fact, if rather than just gauging L mu minus L tau, if I also add right-handed neutrinos, then there is still a non-invertible symmetry. I won't go through, there are just some more U1 factors to keep track of, but what you can find is that, in fact, with right-hand neutrinos, there is still a Z3 non-invertible symmetry. Now it acts like lepton number on the standard model leptons, but it's given neutrinos the wrong sort of charge, such that now there's a non-invertible symmetry that prevents both Majorana and Dirac masses for neutrinos. Now, this is much more interesting because we know quite a few ways in four-dimensional gauge theory to get very small, naturally small Dirac masses for neutrinos. Somehow we need to, if they're Dirac, it's just like the rest of the standard model fermions, but somehow we need to explain that Yukawa is incredibly small in comparison. But following this general reasoning, I'm going to embed L mu minus L tau in some non-abelian gauge group, and I want to find that classically the Yukawa is 0, and it's generated only by instantons, by Tuft vertices. Okay. Now, once you know what you are looking for, in fact, it's relatively easy to write down. You write down the theory that was always, in fact, the beautiful UV completion of L mu minus L tau, and that's to embed L mu minus L tau in an SU3 horizontal gauge theory. I'm just putting the leptons, arranging the 3 generation of leptons into single multiplets under this SU3. They're just fundamentals or anti-fundamentals. And I write down in the UV the charged lepton Yukawa, but there's still a classical symmetry protecting the neutrino Yukawa. And then when I go and quantize this theory, I find indeed there are 't Hooft vertices from instantons of SU3. They're very simple in this case because everything is just a fundamental. So it's a 't Hooft vertex with 2 L lines because L has, the SU2 quantum number, 1 E bar and 1 N. And if I close off the charged leptons by inserting a Yukawa, the charged lepton Yukawa, then I find that these 't Hooft vertices generate for me Dirac neutrino masses, which are automatically exponentially suppressed by an instanton action, 2 pi over alpha, the strength of the new gauge force, from the charged lepton Yukawas. Automatically. And really, this is such a simple theory. I don't want to. I want to get to the new thing because I've spent so much. Indeed, it's so simple that you can. If you have a theory where there's the SU3 stage and then the U1 L mu minus L tau stage before breaking down to nothing, you can get. You run down the instanton generated interaction at the SU3 breaking scale to the U1 scale, which gives you some power law factor. And that actually means if you go to the LHC, and I think I said this even more clearly on the next slide. Yeah, if you go to the LHC or maybe in 10, 20 years at a muon collider, if we discover this Z prime for L mu minus L tau, and we measure the range of the new force, the mass of the Z prime, and its strength, the gauge coupling, then that in fact will tell you the scale at which L mu minus L tau itself emerged from a larger non-abelian gauge symmetry. Because the scale of Dirac neutrino masses and charged lepton masses are so simply related to the other parameters in the theory. All of these we know, or you can measure when you discover L mu minus L tau and you learn the scale of the UV completion. Now, really, I've only generated for you here a scale of Dirac neutrino masses because I've done it with flavor symmetric dynamics of this SU3H. But you can generate the entire texture as you go through the Higgsing from the UV down to the infrared. And in fact, this theory, or a closely related one, was studied by Jim Klein and his postdoc Alonso Alvarez a couple of years ago. Okay, I'm happy to take some questions about leptons or move on to quarks, which is forthcoming work that is not out yet. So with no objections, maybe it's more exciting for me to push straight ahead and ask, what about the quark sector? We wrote down that model of neutrino masses from generalized symmetry breaking. And for some months, I was convinced that there had to be something analogous to say in the quark sector, just because, especially once we've added some right-hand neutrinos, structurally, the two sectors are really parallel, let's say. But it's not immediately obvious to understand what to do. If you try to just copy exactly the same thing, then you'll find that quarks have, as you know, this extra color quantum number that leptons don't have. And that seems to mean that anytime you compute some anomaly coefficient or you look at the 't Hooft vertices that you'll generate, there will be 3 times as many quarks. And so maybe you think, okay, you could generate a 12 quark interaction or something, but that's not very interesting. In fact, what we will require in order to understand what we can do in the quark sector is a more subtle notion of non-invertible symmetry. And the usage will be a bit more subtle as well. No, okay, but before I tell you the answer, maybe just very briefly, I should say, what do I even mean about something to do in the quark sector? I've just told you how to get exponentially small neutrino masses from charged lepton masses, but in the quark sector, we don't really need to generate exponentially small Yukawas. So what do I even want to do? But there is this other puzzle of the quark Yukawa sector, which is strong CP. And because of the time, and I think it's probably true that you guys know what the strong CP problem is. But let me remind you briefly of, good. And indeed, we're going to find that an analogous, although more interesting non-invertible symmetry in the quark sector will point to a model solving strong CP. But let me remind you of the massless up-quark solution to strong CP. This would have been the most beautiful sort of solution, which was could have been in the standard model itself. The idea is that if there is at some UV scale a Peccei-Quinn symmetry that essentially sets the up quark Yukawa to 0, then that means that the strong CP angle is manifestly unphysical at high scales. What you can think is I'm saying that something like rotating U by an arbitrary amount is a good symmetry. And so I can do that freely, but such a symmetry, and the reason I've called it a Peccei-Quinn symmetry, is it has an anomaly with color. So in fact, it doesn't leave the action entirely invariant, but changes it by, changing the theta angle, by modifying adding some FF tilde. And so if you gave me a Lagrangian that had some non-zero theta bar, but it had a good Peccei-Quinn symmetry, I could rotate the up quark by e to the minus I theta bar, whatever theta bar you gave me, and entirely remove it, theta bar, from the Lagrangian. So the point is that theta bar is unphysical. Okay, but even when this was first written down, we knew that in the far infrared, the up quark in fact has an effective mass. It's not massless, but for the same reason that this works, it's a Peccei-Quinn symmetry, it has an anomaly with color. So when you get down to close to the strong scale, when the gauge coupling gets strong and the instantons of the strong sector start doing a lot, those violate this symmetry and in fact generate a mass for the up quark from instantons, right? So explaining why you would still see in the observed hadron masses that there is an effective up quark mass, which is non-zero. But the point is that, and very roughly, instantons themselves don't generate theta, don't spontaneously break CP. And so if you have this good Peccei-Quinn symmetry in the UV, that sets like a UV boundary condition for theta bar. And then it's fine if the instantons violate that symmetry. They don't break theta bar, break CP themselves. They don't regenerate theta bar, but they can still provide a mass for the up quark. So it still works as a solution to the strong CP problem, even if you see an effective infrared mass for the up quark. But the problem is, for decades, this could have been a very good solution, beautiful solution in the standard model itself. But eventually, lattice simulations got good enough that they could tell us, in fact, sadly, QCD instantons do not generate a large enough up Yukawa. If you start your QCD lattice simulation with 0 up Yukawa, indeed, the instantons generate some mass for the up quark, but it's not enough to account for the observed hadrons, the observed mass that we see in the far infrared. So sadly, the standard model itself does not bear out the massless up quark solution and solve strong CP for us. But now we have a new way using some non-invertible symmetry to understand from the infrared when you can find some beautiful model that provides new UV instantons. Okay, and so the plan, what we're going to find is, in fact, a flavor-symmetric massless quark solution to strong CP. in sort of a unification style, which I'm going to continue on, but tell me if you want me to cut off sometime soon. This won't be too long. The point, the way, the more subtle notion of non-invertible symmetry is that, in fact, non-invertible symmetry isn't just about U1 gauge theories, or rather, those aren't the only sort of gauge theories where you find this interesting scenario where you have an anomaly but no associated instantons on a four-dimensional flat space. In U1, indeed, what we saw, there are integer valued instantons. They don't exist on S4 that gave rise to non-invertible symmetry that we just talked about. Now, as we know, if I just have SUN, there are instantons that exist on S4, like in QCD. But if I have some non-trivial global structure, like, for example, with SUN mod ZN, this would be a theory where I only have adjoint matter, no fundamentals, then you have some instantons on S4, the integer valued ones of SUN, but actually these theories have extra fractionally valued instantons. They take values in 1 over n that don't exist on S4. You can only find them, say, on S2 cross S2. You need some 2-cycle to activate some magnetic flux. Well, you can ask me about it offline. But briefly, the amazing realization is that for the quarks, specifically because we have the same number of colors and generations, you can gauge a horizontal U1 that has some non-trivial global structure with SU3 color. If you just try to gauge, the analog of L mu minus L tau, like B2 minus B3, nothing doing. You'll find that same problem that you produce very irrelevant Twift vertices. But if I gauge this particular combination, or you can cyclically reorder them, but let's say B1 plus B2 minus 2B3, again, because minus 2 is equal to 1 mod 3, and because we have the same number of colors and the number of generations, you can gauge this horizontal U1, and it can have the common Z3 center modded out, this non-trivial global structure. Maybe this is even easier to see, and actually how I first saw it was at an intermediate scale. I can consider copying the same non-abelian horizontal symmetry from the lepton sector into the quark sector. We talked about how they're parallel. But if I go in and write that down, this SU3 quantum number, again, the same, put the left-handed guys in the fundamental, the right-handed guys in the anti-fundamental, you'll find the quarks already have that same quantum number. Wow. Why? What reason is that there? And again, the point is that because they have these same quantum numbers, there can be this non-trivial global structure. If there really are no fields that are charged only under the one and not the other, then Wilson lines, which are only charged under one, cannot be ended. You can have this non-trivial global structure. Okay, what does this mean? Well, if I do an analogous approximation like I did in the lepton sector, that the down quark Yukawas are small, then they are protected by, charged under, an analogous Z3 non-invertible symmetry. This is just like we wrote down in the lepton sector. But now the Z3 symmetry, the Z3 one form symmetry, sorry, the Z3 zero form symmetry is intertwined now with a discrete magnetic one form symmetry. In the previous case, it was the U1 one form magnetic symmetry of hypercharge. Now it's a Z3 discrete magnetic one form symmetry that you can have because you can have this global structure. Let me just mention briefly that really understanding this concretely requires you to compute things for fractional instanton backgrounds on some weird spacetimes like I mentioned, and it was very nicely explained by my collaborators Sung Woo and Minho Sun and Mohammed Amber last year in a nice paper. They talked about this more general sort of symmetry that you can have. But the point is, this is, again, this was the infrared understanding. like we had in the lepton case. But what is that pointing you to? It's pointing you to the fact that you can have this really interesting color flavor unification theory, where the 3 colors and 3 generations of each type of quark are placed together, arranged together into fundamentals of SU9. Okay, really, this is a unification style, grand unification style sort of theory, where you're just rearranging the degrees of freedom in the UV, gauging some approximate global symmetry of the low energy standard model. And again, if I can copy the structure from the lepton case and say, in the UV, I only write down the top Yukawa. And so because the bottom Yukawa is missing, theta bar is manifestly unphysical. I can rotate it away. But then again, I have instantons. And now, because I've gone to this UV theory that mixes flavor and color, I have these nice tuft vertices with, again, just 4 legs. And I can close off the up quark Yukawa with the top quark Yukawa and generate the bottom quark Yukawa. Just like in the standard model, you generate some up quark Yukawa from the QCD instantons. Okay, the bottom Yukawa is not exponentially small, so indeed we need a relatively strong coupling in the UV, certainly true. But the point is that you can have these extra contributions, in fact, to all of the down quark Yukawas. And I should say, maybe say explicitly, now that we're doing it in a flavor symmetric way, of course, it makes more sense to start with the top Yukawa and generate the bottom, rather than the other way around. Even though there's this peculiarity of the first generation that flips them. All right. Anyway, the point is that this realizes sort of a flavor symmetric massless down quark solution to strong CP. Now, I do have to tell you a bit more in the quark sector about getting back to the standard model, because, of course, when I have this flavor symmetry, I also don't have the CKM angle. So I haven't, so far in what I've told you, really solved anything. But indeed, you can generate the CKM angle as you go down and break this symmetry from SU9 to SU3 squared down to the standard model, using some vector-like quarks, which can indeed generate some whatever mixing you want, but still don't reintroduce theta bar. In our paper, we're just going to write down a very simple way of doing this that is not the most beautiful. Really, it sort of blows my mind that this theory has not been studied at all. And so definitely thinking about a nice way to do flavor breaking in color flavor unification is needed and would improve our story. But as a proof of principle, we'll write something down. Okay, I'm definitely out of time. Let me go to the conclusion. Sorry for going a bit over. Very broadly, models that you care about as a particle physicist very likely have some generalized symmetries. And I think it's to your benefit to understand them and understand what extra information might be there in the infrared of your theories. And I'll emphasize again that generally you sort of learn more about the UV than you might expect, because violating these higher form symmetries requires new degrees of freedom. So you can learn more about what happens at that UV scale. And in particular, the usage that I've talked about today is that, surprisingly, even though these were sort of right under our noses for decades, theories of gauged horizontal symmetries have interesting non-perturbative physics effects that can provide solutions to some naturalness issues of the standard model. And I do really think that this is just the start of thinking about what generalized symmetries can do for us in particle physics. And I look forward to what more there is to be learned in the coming months and years. So thanks very much for your attention. Sorry again for going over.
Yeah, thank you very much, Seth, for a very interesting talk. So we have time for questions. So I don't think I see everyone, so you could just speak up if you have a question.
Yeah, can I ask Michael?
Yes.
Seth, thank you for very, very nice talk and educational. There was a lot of information new for me, at least. So just to clarify the point you are making about this theta term, in QCD or your solution of so you are starting with certain ground unified scheme where you can basically remove theta altogether, right?
That's right.
And then so then the question is that when you undergo this spontaneous symmetry breaking and eventually you go down to the QCD scale or something like that, there is a extra symmetry which protects from appearing the theta. Is that correct? Or so why the theta from the low energy perspective is not there? Yeah, if I start, for example, just from the SU3 and Koren, and I don't know anything about ultraviolet completion.
Indeed, you good. This is something that's difficult to see from the infrared. But the point is that the UV theory, yeah, and good. I think the way to think about it is that the UV theory sets this boundary condition that theta bar is 0. It's not, as you know, in the standard model, theta bar isn't really technically natural. So it's not quite that there's something protecting it from at intermediate scales. You still have to be a bit careful. I mean, here, good. You're helped out here because the scale at which the instantons come in, this SU9 scale, can be far removed from the scale at which you generate CKM. CKM only is generated after you break the horizontal symmetry. And that's sort of the main thing to worry about in terms of regenerating theta would be the CKM angle, right? And that feeding back in to theta.
I'm talking about, so maybe a little bit rephrase the thing. So so at the ground unified scale, say SU9, you're breaking this ground unification down to SU3 horizontal, right?
Yes.
With this anti-symmetric thing. And so obviously, this theta presumably, in those two sectors, if it appears, for example, should be equal just because of, constrained instanton exchange, right? Which for the massive things. But if I am looking from the low energy perspective, I say I have SU3 symmetry without knowing what is embedded into. So I would have written two different theta terms, right? In general, so associated with SU3H and SU3C. So what is this extra symmetry which forbids that down to 0? So these small instantons, the constrained instantons, presumably decoupled or not.
Yeah. Indeed, it's not obvious to me that you can think about it as good.
So what is the fundamental difference starting from SU3 cross SU3 and writing two different theta terms?
Good.
And the from the vacuum is the embedding one.
The fundamental difference is that you have a UV reason why it had to be 0, why they were both set to 0 in the UV, right? Indeed. I mean, this is, I mean, good. Sorry, let me just say, you could ask the analogous question of the lepton model would be, is there some symmetry of the neutrinos that sort of told you that there was going to be a reason that they were very small. And well, you can think about the non-invertible symmetry as telling you that there can be this UV possibility. But it's just telling you that's a possibility, right? It's not you don't really have the full explanatory power until you are at that UV scale and you see the UV dynamics that indeed gives a direct natural explanation for why that small number was produced. And so I think you want to say analogous sorts of things in this case as well. The usage of the non-invertible symmetry is a little bit more subtle, in part because just always the structure of the massless up-quark solution, that style of thing is sort of subtle and still has some theoretical confusion. I think there isn't a really clear statement about what sort of theories that happens for. But indeed, if you're in this intermediate scale, you can do this non-invertible symmetry analysis, and it will tell you that there might be your infrared theory has exactly the right charges such that you could have a UV theory that provides new instantons. And so in this context, provides a boundary condition setting theta bar to 0, while still providing Yukawas at the UV scale. So
I mean, so this is a symmetry which is essential for understanding this.
I think that's right.
Yeah. Okay. Thanks.
And so can I just follow up on that? So after basically introducing CKM, after basically breaking CP and introducing CKM, you can you still protect it, or you would in principle generate it via running, right?
Yeah, you do generate it. That's true. You are aided by the fact, in general, ideas like this are aided by the fact that the standard model Yukawas, some of them are quite small, so the running can be quite small. But in particular, in this theory, you are aided by the fact, as I mentioned, that the scale at which CKM is generated can be far below the scale at which new instantons come in. And so there's going to be a large sort of power law suppression in terms of like lambda 3 over lambda 9.
Okay, but you would still have from lambda 3 would go down, so that if lambda 3 would be at 100 TeV or something just to avoid flavor constraints, I guess, and you would have the running from there.
Yeah, good. So indeed, lambda 9 should be a bit above. If it's just down at lambda 3, then this doesn't. Then this scheme wouldn't really improve over some similar things people have written down, except that still in this intermediate, well, good. If you don't have the intermediate stage, then there's no non-invertible symmetry, and indeed it's similar to other things people have done. When you do have a separation between these two scales, then you do have this stage where there's this non-invertible symmetry, and you've generated the instantons without yet having CKM, and that can lead to a large suppression in the theta bar that you generate. But yeah, I think I agree with everything you said.
Yeah. Okay, now that's interesting. Can I ask one more thing about the quark masses? So you can generate a bottom, and you said, okay, it's not as pretty probably always, but can you generate all of the quark masses, kind of that, by arranging it?
Yeah, sorry, good. So what I'm generating at the SU9 scale, it's still the flavor symmetric dynamics. So I'm generating at that scale, I'd say you have the bottom Yukawa, I would predict at that scale that the down quark Yukawa is the same as the bottom quark Yukawa is a strange quark Yukawa. So then indeed, as you go down and you break the horizontal symmetry, you do need to be able to produce general mixing, and you can do that using some vector like quarks. In fact, something you should worry about is being able to do this breaking without spontaneously breaking the Peccei-Quinn symmetry. It needs to stay a good quality Peccei-Quinn symmetry in order for the massless quark solution to work quite generally. So you can't so here I have these sigma fields that are breaking the horizontal symmetry. If you just try to couple them, write down some 5-dimensional Yukawa that couples them directly to the standard model Yukawa terms. In fact, they would spontaneously break the Pechi-Quinn symmetry. And nothing would work. You'd have no reason for alignment. So in general, anyway, you want to communicate the flavor breaking through some vector-like quarks, these psi u and psi d that I've introduced. And indeed, I think this is sort of a standard trick with vector-like quarks that I have used. When you have the symmetry breaking communicated through the vector-like quarks, that lifts one Dirac, or in this case, really 3 Dirac fermions worth of quarks, but because it's coming from the SU3 breaking, that can be sort of misaligned from what you might have naively called the flavor basis, and so you can end up producing different mixing angles with the heavier quarks and correspondingly different Yukawas for the standard model quarks. So yeah, indeed, absolutely essential to be able to really produce the observed mixing and masses. I think this is quite generally the right sort of way to do it. As I mentioned, the way we're going to, this very simple way that we're going to write it down isn't particularly beautiful in order to get the very light Yukawas. You're just going to have to do some cancellation. But we're not delving into general flavor model building in this first paper. I think that's absolutely an interesting thing to study in the future.
Okay, fair enough. So but it's basically a generic prediction that you would need those vector-like quarks in that theories to generate the masses.
I think that's right. Yeah, absolutely.
Something which could also then be searched for, but I guess they live at a high scale. At what scale would you need them? So
well, good. Indeed, as you know from flavor changing neutral currents, these probably have to be at something like 1,000 TeV. Actually, I studied this breaking scale because in some sense it's simpler, but I think probably the more profitable scheme would be to break SU9 directly to SU3 cross U1 mod Z3. Because that U1 doesn't introduce flavor changing, it doesn't couple off diagonally to the quarks, right? The U1 couple B1 plus B2 minus 2B3. And so I think that can be at a far, far lower scale. And hopefully the dynamics associated, I had, good. Somehow I at least from a cursory look, I don't think I've found actually the constraints of what this particular Z prime sort of charge, what that should be. But certainly at a far lower scale, so you could hope to actually look for this at a collide. I would be very interested to understand the details in that breaking scheme as well.
Yeah, thanks. Are there other questions? I have another one. So in the beginning, when you introduced those higher form symmetries, they were all, I think, U1 symmetries, right? Abelian symmetries, at least for electromagnetism and so on. Can you have a non-abelian higher form symmetry?
No. This is very interesting. Indeed, good. I'm not in a good position. Easiest to explain at a blackboard, but in particular, it's only for a zero form symmetry. It's something that acts on the charged operators are 0-dimensional, and so the symmetry defect operator that I'm drawing here is 4 minus 1 minus 0 or 3-dimensional, because that's in general what links, what has some topological linking a point and a three sphere. And in this particular scenario for zero form symmetries, you can have an ordering of these symmetry defect operators. So it makes sense to act first with one three ball and then with a larger one or something like that.
Okay.
You can
Okay.
Now it's very difficult for me at least to think in 4 dimensions. But when you have a one form symmetry that acts on line operators, so now the symmetry defect, it will act on line operators, one dimensional. So the symmetry defect operator is 4 minus 1 minus 1 or 2 dimensional. It's difficult for me to see this visually, but such 2-dimensional surfaces in 4-dimensional space-time do not have such a notion of ordering.
Okay, and therefore you can always
them.
Commute them, basically.
Exactly.
Sort of.
Exactly. There's a nice picture. I should recommend my collaborator Sung-Woo Hong and Daniel Brennan, who used to be a postdoc at Chicago, is another fantastic physicist. They put out some notes on generalized symmetry recently, and I think they include some nice pictures illustrating this, that fact. But indeed, yeah, the higher form symmetries are always abelian.
Okay, good. Thanks. Thanks also for explaining it there.
No, my pleasure.
Yeah. Any other questions?
Seth, may I ask the question? So you are looking for this breaking, through the instantons or whatever abelian instantons of the generalized symmetries. What type of symmetry breaking is that? Is that the you would call explicit symmetry breaking? Are there some kind of eta mesons associated with those breaking, or
no, I'd say yeah, sort of from the bottom up perspective, you can think about this as explicit breaking of the magnetic one form symmetry. Yeah, that's right. But I don't think there's any associated mesons or anything that you get.
So that's a gauge symmetry in essence, right?
No, a one form global symmetry.
Yeah, the global symmetry. What?
Yeah.
Why the Goldstone theorem fails to work?
Oh, well, sorry, it's explicitly rather than spontaneously.
Oh, sorry. Yes. Okay.
Yeah.
Well, I mean, we have a similar thing in QCD, for example, with the eta meson, which is not quite a Goldstone boson in a sense. However, in a large NC limit, you can consider that as a Goldstone boson, right? I love it. And
yeah.
Not sure.
No, good. So there certainly is a Goldstone theorem for higher form symmetries, and in fact, you can view the masslessness of the photon, the familiar photon, as being the result of the spontaneous breaking of the magnetic one form symmetry by the vacuum of 3D. You can sort of view the Goldstone as. You can view the photon as the Goldstone of the one form symmetry spontaneous breaking. Yeah, but the approximate
this is like anomalous symmetry, more like anomaly breaking, right?
Yeah.
Draw the analogy.
Yeah. It's a good question about the analogy to the eta prime. I'm not sure I have anything very useful to say. I mean, you might want to consider sort of the heavy gauge bosons as being
something like that. Yeah.
Analogous.
I'm not sure. I'm just.
Yeah. No, it's an interesting thing to think about. Yeah, indeed. I mean, in general, I think that I think a lot of the language about breaking these symmetries and how they fit into effective field theory hasn't fully been developed. is an interesting thing to think about. Yeah.
Okay. So
Great.
I think
Yeah.
we exhausted the questions. Yeah.